1, 2, 3, 4. Hey everybody, this stream is starting up. So today we're going to cover exponential functions. That doesn't sound good. Exponential functions. Okay, good. The deal with an exponential function is that, well, we're talking about it. We've been talking about it all this time, but you didn't know it. So let's do it formally. So by the end of this video, you should be able to recognize which numbers are good to use as bases in exponential functions. There's a hint. You'll understand the shape of an exponential graph. We're going to talk about graphing them. And then you can locate attributes of it. The y-intercept and the horizontal asymptote, those are both parts, foundational parts of the exponential graph. And then you can locate them in a composite function. So I'll teach you how to graph composite functions. Okay, let's go. So we've been talking about exponential expressions. An exponential expression is one that looks like this. Minus 5, or 2 to the minus 1/2. Hold on. 2 to the 0, say 2 to the 1/4, 2 to the 1, 2 to the 2, 2 to the 4. Those things, right? And each of these has a value. So, 2 to the 4 is equal to 2 times 2 times 2 times 2. I taught you how to punch it into your calculator. That should equal 16. 2 to the 1/4, that's equivalent to the 4th root of 2. Let me take that on my, that's 4 cube root 2. Which is apparently 1.189207. You know that 2 to the 0 is equal to 1. 2 to the minus 1/2, that's equal to 1/2 square root sine it, 1 divided by square root 2, and 0.707106, whatever. Okay, so the long and the short of it is that no matter which number I write up here in the exponent, it corresponds to some actual number. How to interpret the number, whether it's positive or negative, whether it's a whole number or a fraction, we talked about how to interpret that in a past video. But the result here is that we can interpret, regardless of what number you put up here, there is an interpretation where this is equal to some number. So we can think of this expression in terms of a function. Where the function is composed like this. If you want to know what f at 1 is, I'm just going to replace the x with a 1 and then evaluate it. F at 0.5, replace the x with a 0.5 and then evaluate it. 2 to the power 0.5, 1.414213. Okay? So in other words, because we now know that we can just replace that with any particular value and there's a good interpretation for what that number is, we can treat this as an input-output system where you tell me what the value of x you want me to put there, and then I calculate the corresponding value. So we think of that as a function, and it's called an exponential function. Okay? So before we say anything else about exponential functions, and we're going to be talking about graphs, we need to note here, generally exponential functions have the following form. Ax, where a is a number. The value x is the value of the input. The value y, that's the output, like usual. But a is just some number, any number you want it to be. But it can't quite be any number. And the reason has to do with what the value is as an output. Okay? Because we want the input x to be any number. Any number including, for instance, x is equal to 0.5. And what this does is it means that the value of a can't be any possible number. The reason's simple. Okay, so like if a is equal to, say, -3, how about -4? If a is equal to -4, terms like this, a to the 2. All right, so like -4 to the 2, that's well defined. That's -4 times -4, so that's +16. We're cool. On the other hand, the function, if the function at the value x is equal to 1/2, that corresponds to the square root of -4. That doesn't exist. So the deal here is that if the base of our exponential, that number, if we allow negative numbers to go in there, you're doomed, because there are lots of numbers that have like roots in them, even roots. So there are lots of, long story short, all we do is we say, okay, a isn't just any number. A has to be a number that's bigger or equal to 0. It's not allowed to be positive. It's not allowed to be negative. If it's negative, you're doomed. So like there are some exponential functions like y is equal to 0 to the power x. This is just 0. So we don't even really talk about this as an exponential. So for the most part, we only refer to exponentials in terms of a being bigger than 0, because that, you have some interesting behavior there. Okay, so long and the short of it is an exponential function is an expression like that. It's going to be some constant to the power x. And that constant is going to be a positive number, because if it's a negative number, then there's going to be some inputs where the output doesn't exist. And we want, in this case, the function to be defined for any possible value of x. Okay, so with this in mind, exponentials have a very characteristic behavior and shape. Functions have a characteristic behavior and shape. What is that? It looks like this. Oh, geez. There we go. Well, something exciting's happening outside my door. I think the custodians are here to clean the office. We'll see. So I'll explain why they behave this way in a couple seconds, but here's what you need to know about them, basically. They all have the same shape, so if this is y is equal to 1, 2, 3, 4, all the exponentials in the world, every exponential for any value of a, they all kind of look like this. Okay? As x becomes more and more negative, the line's going to get closer and closer and closer to the x-axis, but never touch it. We call that attribute a horizontal asymptote. Oh, you're the custodians. Hey guys, how's it going?
How are you?
I'm good. I'm recording a lesson on my thing right now.
Sorry, that's alright.
It's alright.
We'll come back then.
I'm gonna be here a while.
Next week?
You guys can skip it this week.
Okay.
It's okay. I don't think there's any garbage on the floor.
Have a good weekend.
Have a nice weekend. There's a horizontal asymptote. We call this part the horizontal asymptote. And then it gets really big really fast on this side. You've probably heard of exponential growth. Oh, the virus is increasing exponentially. That means it gets big real fast. It gets big real fast in a characteristic way. But, you know, so it's uppy on this side, and then it approaches the x-axis without ever touching it on this side. And then there's a third characteristic, which is it intersects, its y-intercept is equal to 1. I'm going to draw a bunch of different exponentials, just characteristically we can talk about their different shape. So this might be, say, I don't know. I haven't labeled the x-axis. But if I were to draw some other exponentials, they kind of look like this. There's maybe one like that. And it gets up really big. And another one like this. It's always lower. And then it's always higher. Okay. Big faster. All these exponentials are going to go through the y-axis at the same place. One exponential, say y is equal to 2x, might differ from another exponential, y is equal to 3x, or a different exponential, 10x. All of these are going to differ in terms of how quickly they go up to the right and how quickly they approach this horizontal asymptote, but they're all going to intersect the y-axis at the same place. Let me explain why that's the case. It's because the y-intercept is where x is the location when x is equal to 0, and any exponential expression you have is going to be 1 there. 3 to the 0 is equal to 1, 10 to the 0 is equal to 1, right? And that's why all these graphs are going to have the y-intercept in the same place. Okay, so let's talk about generally the shape of these. It doesn't just go up and it doesn't just go down. It does this for a specific reason. So let's talk about that. What their behavior is like. Exponentials, functions double or triple or quadruple over regular delta x. What do I mean by that? I mean like 2x, right? So this is a function that's going to go from 1 to 2 to 4 to 8 to 16 to 32 to 64, right? 3 to the x, this is a function that's going to go 3, 9, 27, 81, etc. Or y is equal to 4x, right? So the idea here is that as x increases, every time x increases by 1, the value of y is going to double in this case. Let me sketch the value of this function, this specific function, and we can have a better sense of it. So y is equal to 2x. Let's get our axes straight here. Oh, come on, be nice. Let's try that again. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I don't like that spacing. What if we just go to 8? 1, 2, 3, 4, 5, 6, 7, 8. Sure, that's good. And then 1, 2, 3, 4. So that's the x-axis. Here's the y-axis. 2, 3. minus 1, minus 2, minus 3, 1, 2, 3, 4. Okay, good. So let's start plotting this by just evaluating it at some points. So when x is equal to 0, y is equal to... Oh, I didn't even write this exponential very good. The x goes up here. When x is equal to 0, y is equal to 1. When x is equal to 2, y is equal to 1. Hold on. When x is equal to 1, x is equal to 2, x is equal to 3, x is equal to 4. Y. So when x is equal to 1, y is equal to 2. When x is equal to 2, y is equal to 2 times 2 is 4. When x is equal to 3, 2 to the 3 is equal to 8, 16. All right, so where are these points? First point is right here. When x is equal to 1, it's equal to 2. When x is equal to 2, it's equal to 4. 1, 2, 3, 4. When x is equal to 3, it's equal to 8, 4, 5, 6, 7, 8. All right. So to sketch the graph, it'll probably look something like this, and then it goes off my graph. Okay? And all I've done is connected the points together. I want to emphasize that whole doubling thing. So here's the deal. Let's draw a vertical line from the x-axis to the graph at each of these points. Okay? So the deal here is that this line, it's one step over. This line is twice the height of this line. It was originally 1, and now it's twice as big. And then one more step over. It was originally 2, and now it's 2, twice as big as before. So now it's 4. 2, 1, 1. This one, how much higher was it than it was before? It's going to be 4, 4, twice as high, etc. So you can imagine how high it's going to be here. It's going to be this high, so that's 8 plus another 8 there. Okay. So the interesting thing about this particular explanation is that it works back or forward, right? So if I knew that it halved, if I knew that it doubled every one step, you could keep drawing it to the right over here. Double, 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 right? If on the other hand I move backwards, you see that it's exactly the same pattern, but you talk about it halving, right? So it goes from 8 to half its length. Now it's 4. And then one more step over, it goes from 4 to 2, half its length, 2 to 1. And this progress lets us say, okay, so here, one step to the left, it's half the height it was the origin. It's 1/2 high. And then it's a quarter. And then it's an 1/8, etc. So it goes by half. Its height halves. Its height halves. Okay? Now, what this does is it explains the shape of the exponential. The idea here is this upward curving shape that gets bigger and bigger and bigger. Its shape is defined like that because its height keeps on doubling, or tripling, or quadrupling. But it can always be described as doubling over regular spatial intervals of x. On the other hand, it also explains why it has a horizontal asymptote. The idea here is that you're always having the height, right? The height at each successive point is half the height of the point to the right of it. And so, you never get down to 0. You'll always have a little bit left. And even though you always have a little bit left, you're never going to cross the x-axis. So this gets closer and closer to 0 as that height gets smaller and smaller and smaller, but it's never going to cross the x-axis, and that makes it a horizontal asymptote. Okay? So, the deal here is that if instead I was graphing y is equal to 3x, what I would do is you would start here, and then you would go multiply by 3. So your original height is 3. And then on the next step, you would multiply by that by 3. So the original height, 1, 2, 3, the original height, 1, 2, 3, and then the original height. So 3, 3, 3. You would triple it every step for this one. And that would give you a line that comes, that was a pretty bad graph. Give you a line that comes up much faster than its predecessor. On the other hand, as I draw it on the other side, it goes down by a third. So the first height is a third of the original. So it's a third, and then a ninth, and then an 18th. So you see that it has descriptively the same behavior as x over 2. The purple one and the red one have the same shape. The big difference is the curve, whether it's going to curve up strongly or less strongly. In any case, it's always going to curve up kind of strongly, and it's always going to flatten out approaching the y-axis. And so how it does so depends on what the base is specifically, but that's all it depends on. Fairly simple. So let us review what I just told you, because there's something fun. Hold on. Yep. Review. Y is equal to a to the x. So, as the input to the function, all right, hold on. This increases regularly by a factor of a. Okay? And as the input to the exponential function goes to minus infinity, the y goes to 0. That's the horizontal asymptote. Okay. At x is equal to 0, y is equal to 1. We know that they all cross the y-axis at the same place. Because it's increasing by multiples of a, at x is equal to 1, y is equal to a. And so it gets large on one side of the axis and it goes to 0 on the other side. So it looks like that. And you know, we're going to shortly see exponentials that look like that as well. So let's talk about how to sketch composite exponential functions, because that's pretty much the activity I want you to learn how to do right now. What's a composite exponential function? This is what we're talking about. Okay, so composite functions. All right, well, let's review composite functions. One function is that. Another function is our exponential. This weird expression is what happens if you put one function inside another function. So it's 2 to the f of x, which is 2 to the 3 plus x. it's important to distinguish when we labeled all the properties. We made a note that it's not increasing with respect to x. It's increasing with respect to its. Whoops, that's not the right x. That's a time symbol. Its behavior depends on what the input to the function is doing. I labeled that for a reason. It's because we're going to move on to exponential composite functions. So this is the input. So the value I'm inputting into the exponential is the output of this function. Okay. So in other words, how are we going to graph it? Essentially, sketching a graph of this consists entirely of figuring out when all these things happen. Figure out for which value of f, value of x, the input to the exponential is equal to 0. What happens when the input to the exponential is equal to 0? That's the y-intercept. Okay. So in other words, I take this expression up top here and I ask which values of x make that equal 0? And the answer is x is equal to -3. What does that tell me? It tells me where the function is going to cross the x-axis. It's going to happen at 1, 2, 3. Right? Oh, wait. Calling it the y-intercept just struck me that that's super confusing. So what we're going to say here is, ordinarily in your basic exponential function, the y-intercept is y is equal to 1. It's y is equal to 1 on all these. You know that when x is equal to 0, the input of the function is 0, the output is equal to 1. So essentially that's what we're asking. We're saying, at what value of x is the input to the exponential 0? At that value, y is equal to 1. So now you know that at x is equal to -3, the height of this function is +1. Step 2. That's not how you spell which. Which direction actually, you know what? I'm gonna cut a step out of the notes I've written. For which value of x is the input equal to 1? So 3 plus x, I want the input of the exponential to equal 1, because I know that at that value, y is equal to the base of the exponential. So that's going to happen at x is equal to -2. So I know on this graph at x is equal to -2, the height is equal to 2. Okay. So then all I have to do is I just have to, if I want to, I can do that doubling game, and I can be like, okay, double here. So now it's up to 4, and now it's up to 8, but I don't really need to do that. All I need to do then is just sketch a line through it. Because I know the general shape of the exponentials. These 2 points tell me which direction the shape is going. Where it goes through there. Is it going up or down as I move to the right? Which direction is the horizontal asymptote? Horizontal asymptote in this case is moving to the left. I want to ask when the input goes to -∞, because that's the horizontal asymptote. Alright. Sorry, my lecture notes for this are super weird. I don't know. So, to review. to review. The shape of an exponential is either going like that, where it has a horizontal asymptote on one side, and then increasing on the other, or it can also have a horizontal asymptote to the right on the right and increasing to the left. It's always got one of those two shapes. So then when you get your composite function that you're trying to graph, we always ask ourselves 2 points. All I need to know is where 2 points are together to figure out whether it's shaped like this or shaped like this. And so I'm going to figure out where f of x is equal to 0, because at that point y is equal to 1. And I'm going to figure out where f of x is equal to 1, because at that point y is equal to the base of the exponential, in this case 2. And those 2 points are sufficient to tell me which direction it's going up or going down, and that's all I really need to know if I'm going to sketch a graph. Let's try another one. Alright, how about this one? Y equals 3, 1 minus x. Okay, so first I want to ask myself if where this thing, the input to the exponential, is equal to 0, because I know that at that location y is equal to 1. So that's going to happen at x is equal to 1. So I make a note here. 1, 2, 3, 4, and it's going to equal 1 there, so I put a little x on my graph. And the second thing I want to know is where the input to the exponential, where that thing is equal to 1, because I know that at that point y will equal 3. So that's going to happen when x is equal to 0. So I know when x is equal to 0, y is equal to 3. 1, 2, 3. Okay. So you know that the graph, so then you just connect the dots with the graph of the appropriate shape. It's going to have a horizontal asymptote to the right and blow up to the left. Wait, what does that mean? Hold on. Isn't this weird? I thought we said this is a thing that doubles every time. What's going on here? You might ask. You might also ask why this graph is so ugly. We try drawing it again. There, that's a fine graph. Okay, so why is this the regular shape but switched around? Like, what's up with this weird shape? I can answer that question by rearranging my my equation. I want you to remember that this number here can be any value, positive, as long as it's positive, and that means it can be less than 1. I can write this expression as x to the 1 times 3 to the minus x if I want. That 3 is a pretty fun thing there. Don't worry about it quite just yet. But you can write this as 1 over 3 to the x. This term becomes this term, right? It's negative, so it's reciprocal. So this is an expression, instead of doubling every step, this one decreases by a factor of 1 over 3. Okay? So every step I take to the right, it decreases by a factor of 3. So you divide it by 3. You divide it by 3. Yeah? And the result is a horizontal asymptote. On the other hand, if you move to the left, that's like multiplying by 3 times 3 times higher, 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 and then this thing gets taller and taller and taller. Okay? So, yeah. But, so that explains its shape. You don't really need to worry too much of it because the 2-point explanation for how to sketch a graph, it works for these. Let's try another one, and then I want to explain something really cool to you. Okay. So maybe try this one yourself. Y is equal to 2, 3 plus x. Oh, come on. So sketch the graph while I sketch mine, and then we're going to talk about something really neat here. Are you sketching? Or are you just watching me work? Get to work. What do you mean you can pause the video and you don't need to watch this? Well, drawing these X's takes a while. Okay, so I want to ask myself about this term. We know that y is equal to 1 when 3 plus x is equal to 0, so that's x is equal to minus 3. So at x is equal to minus 3, y is equal to 1. And then y is going to be equal to 2 when 3 plus x is equal to 1. So that's at x is equal to minus 2. So that's right here. Okay. I'm going to sketch this using the doubling property just so you can see what I'm on about here. So this is 4, and you go up another 4. 1, 2, 3, 4. Whoa, wait, hold on. Hold on. This one's 2. So that's 1, that's 2. Now the next one's 4. 1, 2, 3, 4. So that's going to be 4, and the next one's going to be 8. 1, 2, 3, 4, 5, 6, 7, 8. 8. And the next one's a half. So here is a really nice graph of the function. Now, for fun, let's compare that with the function y is equal to 2 just to the x. Okay? So we know that that's just a basic exponential, so it goes through that point, and then it doubles, and then it doubles again, and then it, get out of here, you. And then it doubles again. There. And then, good. And then it goes down by half, and then a quarter. Okay. Let me try to draw a graph of this. Okay. Are you ready for the cool part? Because I want you to see something in relationship to these two functions I've just written. I'll call this one f of x, and I'll call this one g of x. So this here is the graph y is equal to f of x. This one's y is equal to g of x. That's not the fun part. This is the fun part. I can write this as 2 to the 3 times 2 to the x, or 8 times 2 to the x. In other words, this one graph is always 8 times higher than the other one. And certainly that looks to be true. That one's 1, and this height here is 8, right? This one is a half high, and this one here is 4 high. So that relationship is definitely true. But there's something else really cool about this. if I take this line, you know what? Yeah. If I take this line and move it, ooh, geez, sorry. If I move it, oh wow, there's two functions here? Okay. If I move it 1, 2 steps, 3 steps to the right, it's the same graph. Isn't that bonkers? And the reason for that is that if you think about it, this function is a composite function of this one. And all building a composite function in this way does is I've shifted the value where instead of being 0 at x is equal to 0, being 1 at x equals 0, I've just shifted it over by 3. Yeah? Because it's 3 plus x. So I've increased the input to the exponential function by 3, so if I move 3 to the left, you get your original function, which is bonkers. So in essence, this graph over here and this graph over here have the same shape in two different ways. One of them is that if I transport the graph to the right, ooh, come on. If I transport the graph, oh geez, I don't know what I'm doing anymore. Hold on. If I transport the graph to the right, it's the same shape. And the other is, ooh, if I multiply this red one by 8, you get the yellow one. It's the same shape in two different ways. Isn't that bonkers? That's a special property that exponentials have. Anyway, so that is the thing on exponential functions. It's a function, exponential. Whoa, I don't know what's going on here. It's scrolling up for no reason. Hey, stop. Oh, geez. Okay, well. I don't know. Okay, well, just stop scrolling, yo. Alright, how about this? Tick. Oh, geez. Alright, so that was very dramatic. Let's review the basic properties. First off, exponential functions look like this. A to the x. You'll note that the output of it is always going to be bigger than 0. And the reason the output is going to be bigger than 0 is it's the same number multiplied by 2 a whole bunch of times, or multiplied by 3 a whole bunch of times, or multiplied by a whole bunch of times. And as we discussed, the value of a has to be bigger than 0. It's also a function that has a horizontal asymptote. So it blows up on one side and it goes to 0 on the other side. And the reason is, as I move to the right, I'm multiplying by a each step. And I move to the left, I'm dividing by a each step. Okay? So to graph it, I just need to figure out where 2 points are. The point where y is equal to 1 and the point where y is equal to a. And those are the ones where the input is equal to 0, or where the input to the exponential function is equal to 1, respectively. Once I know where those 2 points are, I can sketch my graph. Okay, so one of the most important things here is to understand that exponential functions are all about doubling, or tripling, or quadrupling. Or always about doubling, or halving, I guess, but increasing by a multiple, same time, over and over and over and over. You see it in a bunch of biology for that reasons. Like if you have bunnies on a hill, every month each bunny is going to have more bunnies to greater or lesser extent. And so the numbers are going to multiply in this way. Exponential increase is one of the fastest ways to increase something. It's faster than any polynomial in the long run. All right, that's it for today. Sorry about that. weird scrolling bit.